Welcome, everybody. I am super delighted to introduce you to Michael Hecht. He is trained as an experimental scientist. Can't wait to find out more about that. And he constantly seeks to combine his expertise in development of instruments with scientific exploration. So get this, he is not only the principal investigator of MOXIE, the Mars Oxygen ISRU experiment, but he is also part of the management team for the Event Horizon telescope that images supermassive black holes. So he is at MIT. His team has worked hard on this amazing instrument that is on Perseverance. He's going to tell us more about that. And occasionally he breaks out the clarinet and plays a bit of klezmer music. So, Michael, we're so delighted to have you.
And I'm delighted to be here, Janet. This is, as I like to tell everyone who will listen, going to Mars is an expensive and complicated proposition. We do not do it just to enlighten each other, the few hundred people on the science team. We do not do it to enlighten a few people up in NASA headquarters. We do this for the world. So any opportunity to talk to that world, I'm grateful for the opportunity. So thank you.
Well, it's like, let's start with the name MOXIE, because not only is it, as we know, everyone loves a good acronym, but it also has some other meanings and maybe some other origins. Would you like to talk about what those are?
Oh, I'd be happy to talk about that. I'm a native New Englander. I'm from the Boston area, and I'm now working up at Haystack Observatory, which is up in a town near Lowell, Massachusetts. For 36 years, I was living in California, kind of in exile. And finally, my family decided it was time to move home. And I found this wonderful position, Haystack, which is kind of how I ended up in these two worlds, going to Mars and doing black holes. Okay. And now, but I remember MOXIE, the soft drink, from my childhood, when in fact, in this area, we didn't call it soft drink. We didn't call it soda. We didn't call it pop. We called it tonic. And the reason we called it tonic is because the first big soda here was MOXIE, which was a nerve tonic originally, until they found they can make a lot more money by carbonating it and adding sugar and selling it as a drink. But it still was always tonic, and I think in parts of Boston to this day, tonic. MOXIE was big here. And you can see some of the MOXIE paraphernalia. You might see what I'm wearing. If it's high enough, drink MOXIE. And it's not well known elsewhere in the country. Now, MOXIE was invented in the 1880s, I believe, in Lowell, Massachusetts, just down the road from Haystack Observatory. It is now the state drink of state Maine, and where it's still very big. And in fact, it's the state drink, and they have, to celebrate that, an annual MOXIE festival. I suspect they didn't do it this year, where they get tens of thousands of people. And one of my biggest thrills working on this mission was I was invited a few years ago to be the Grand Marshal of the parade at the MOXIE Festival. What a kick that was. So it's all about MOXIE, and the tie-in, there's two tie-ins. One is that we did not expect to win this opportunity when we proposed it, to be honest. It took audacity to do it. It took what we like to call MOXIE. Why do we call it MOXIE? That name actually came from the soft drink and was popularized in sort of advertising, that you've got MOXIE. And the word stuck better than the soft drink stuck. So we felt it was the perfect name for an audacious proposal. And the fact that we're taking carbon dioxide and doing something interesting to it is kind of reflected in the fact that this was one of the first carbonated beverages sold in the United States. And that's another useful application for carbon dioxide. Okay. So lots of tie-ins, and the acronym works, of course. You mentioned ISRU. I don't know if your audience knows what ISRU is. It's a typical.
I'm glad you said that, because I remember the first time I heard it, and I was like, let me find out what that is. So yeah, talk to them about what we mean by ISRU. If you're like, what did they just say?
Yes, yeah, I'm happy to. It's a typical NASA acronym, and in that it's short for something that's equally unintelligible. It's short for In-situ Resource Utilization. So let's kind of break that up. In situ means in the place where you find something. Resources, well, we kind of know what resources are. They're things you can use. And utilization, well, that means to use them. So what are we really talking about? We're talking about living off the land. That's the common expression. And I like to say that, NASA could have made an acronym LOL for living off the land, except that was already being used for something else. Okay. So we got ISRU instead. We got second prize.
You know what? One of the best, I think, ever explanations of ISRU. So thank you. What I want to know is, let's go back to your team and how you won the contract. I mean, this is a profound instrument. And when it works, you guys have experimented, you know that it works here, but when it works on Mars, it's a game changer. Human exploration looms ever nearer. So talk to us about starting that process, what those conversations were like, and then tell us what MOXIE does.
I'd be happy to, because it really was interesting and different. And as you say, it's a game changer. It will bring the days of human exploration closer, which is why I'm doing it. It's a bit of a change for me. First of all, when I say it's a little different, usually what NASA does when they mount a mission like Perseverance is they say, we're going to Mars. We have a general theme. We want to look at things microscopically, do analysis microscopically. We want to select samples for sample return, which is the focus of the mission. Our general theme is looking for signs of life. Now propose an instrument. And that's all they say. And you could propose a microscope, you could propose a spectrometer, you could propose a camera, all sorts of things. But for this opportunity, there was another partner, okay? And that other partner, instead of being the science folks, what they call the science directorate at NASA, it was the human exploration people, the human exploration directorate, and the technology, the space technology directorate. And they worry about, the space station, and they worry about rockets and things like that. They got involved because they felt it's time to start getting ready to send people to Mars. Maybe some of the people listening today. Not me, I'm too old, but there may be some that will be there. And when they did that, they said, but we know exactly what we want. We don't just want, give us something that will help human exploration. We want something that will demonstrate you can turn carbon dioxide into oxygen, because that's a big problem for us. So we were told what to propose. And we proposed against people with a lot more experience in it than we had. And honestly, I think getting the right combination of people was really what did it. This was an odd case. Even though I'm the principal investigator, I was approached to lead this by people I know, by friends and colleagues, said, Mike, you're the guy to lead this because in part of my experience, I've worked with the human exploration part of NASA, the folks that want to send people from Mars, even though that was tiny. I've worked with them for literally decades. And I've sent instruments to Mars before, especially on the Phoenix mission. So, there was a good rationale that my experience was well suited to this, because you not only need to convince them that you can do it, but that you really have bought into their objective. My partner, and I have great technology people at JPL who were the partners that developed the instrumentation. And my partner at MIT is an old friend and mentor by the name of Jeffrey Hoffman. Okay. Now, and you probably know Jeff. When I say old friend and mentor, Jeff was actually my, when I got my master's degree at MIT, he was my advisor. He directed the work, and that was a lot of years ago. That was a lot of decades ago. I went off and did what I did. I've told you about. Went off, became an astronaut. He has flown 5 trips on the space shuttle. He knew what it takes to send human beings, to send people out into space, and how to deal with the risks, and how to deal with the needs, and how to make it work. So he knows that. So we had a combination of me, I've sent stuff to Mars. I've worked with those the human exploration folks, and Jeff, who's, if you will, walked the walk, except the walk he walked was in space. Okay. And great technology partners. And I think that's a lot of the reason we won. I'd like to think we had a really solid technical proposal as well. But I think we convinced them this was the right team to do this work.
Because we need to explain to everybody, Mars's atmosphere is what, 96% carbon dioxide. And
that's
so
right.
There's, you're not like we've all been in an analog this last year. You're never going to walk out on Mars unless there's a MOXIE 5000, kind of like making breathable oxygen out there. But we're not just talking about that it can maybe convert this MOXIE, convert the carbon dioxide into oxygen. It can be both oxygen for astronauts, but even more important, that rocket fuel, right? Talk about what that process is.
No, that's absolutely right, Janet. That's the important thing. There is not only an atmosphere that is almost entirely carbon dioxide on Mars, but there's precious little of it. Okay, if you were to take a ride on a high pressure balloon, about the highest on the Earth you could go is about 100,000 feet. 100,000 feet, 20 miles up, and at that point there's very little air. But there's about the same amount of air as you would find on Mars. Okay, and you would not be able to breathe. You would need a protective suit. Very little of it. Now on Mars, not only is there very little, but it's almost entirely carbon dioxide. And that exposes something that we almost never think about, okay? And that is that everything from us as people to our cars, to our fireplace, our campfires, to our jet planes, to our rocket ships, all have to breathe in order to burn fuel. Now you say, what do you mean we burn fuel? Of course we burn fuel. We call it food, but it's fuel, and we burn it. And the way we burn it is we breathe in and out, and that gives us oxygen. And as we know from a flame, you cannot burn a flame without oxygen. If you cover up a candle in a jar, it will go out because it needs oxygen, and we need oxygen. Now, when I say burn, I'll put that in air quotes. I don't mean a fire, but I mean if you get a chemical reaction that turns that fuel into energy, okay, that's when you have to breathe. And okay, now then compare a person, even 4 people, breathing to burn fuel, to a rocket ship taking off from Mars. And my God, that is breathing 1,000,000 times more. And that's not hyperbole, that's about the right number. 1,000,000 times more than the people are breathing. It fortunately only does it for a few minutes. But even so, if 4 people in our audience here are the first 4 people on Mars, and I often ask this in person, who wants to go to Mars? And a lot of people raise their hand, and then I say, and who wants to come home again? Right? And most of them look puzzled and then kind of gently raise their hand. If you want to come home, you have to take the rocket, and that rocket needs fuel, of course. But rockets, unlike jet planes, unlike fireplace, unlike us, can't just breathe in that oxygen. They have to take it with them, and that's why those rocket ships have such huge tanks. They're mostly full of oxygen. And the oxygen is the heavy part of the fuel. Okay, the fuel is the light part. The oxygen is the heavy part. So if you want to come back again, you need, if there's 4 astronauts, something like 25 tons of oxygen. The whole crew won't use more than half a ton in the whole mission, which is a year and a half long. But the rocket, that needs 25 tons. And that's to burn 7 tons of fuel. So boy, bringing all that from Earth is a daunting, it's a daunting prospect. I mean, because don't forget how much fuel you need to lift off 25 tons of oxygen into the sky just to take it to Mars. It's enormous. So that's why we need to make it on Mars. And sure, we can use some for the astronaut to breathe, but they're breathing a little bit compared to what the rocket is breathing. Sorry, that was a long explanation, but that tells you why we're focusing on this.
No, it's profound. Tell me a little bit about when it's on Mars. How long will it run? It's like once it goes successfully and as planned. It sounded to me when I was doing the research on it that it will capture it. You'll get about an hour's worth of O2 or an hour's worth of production, and then whatever that O2. Then do you have a release valve, or it gases off and then you're going to try it intermittently during the mission? What's that process like?
Okay, well, let me tell you what that's all about. You're absolutely right. And we would love to put on Mars exactly the unit that we plan to use when we send astronauts. And when I say when we send astronauts, the way you do this, just the way you send astronauts to Mars, okay, is first you get ready for them. So you, what they call pre-deploy, many months in advance, all the things they'll need. I sometimes call it the B&B, breakfast. You bring the habitat, you bring a power plant, you bring rovers, you bring everything, and you bring oxygen for the ascent vehicle. You bring all that first, and when that's all ready, you tell the crew, okay, now you can go. Now we're ready for you. Just bring your toothbrush and your suitcase, and we're ready for you. Okay, so that's what we need to do. And to fill up that tank of oxygen so that they can come home again. Okay, so your 4 people in your audience can come home again, is going to take us making 2 kilograms, at least 2 kilograms of oxygen per hour, every hour for about a year. Okay, that's a lot of oxygen, 2 kilograms an hour. What MOXIE can do is 6, maybe 10 grams an hour. Okay, so it needs to make 200 times more to support the human mission. And I'd love to be sending that big unit. The problem is, well, first of all, it's big and the rover's little, okay, so we can't fly a big one. But the bigger problem is that the rover is powered by about 100 watts of power. It's, it's what used to be light bulbs before they all went to LED, right? It used to be 100 watts. That's it. And what we're going to need for the real deal when we fly people is we're going to need 25,000 watts, not 100 watts, 25,000 watts. And so we don't have a big power plant like that on Mars now. So we have to settle for a little tiny scale model. It's about, this big. Well, I'll tell you, it's exactly this big. Except it's in a case that's all shiny and gold, but it's this big, if you can see it. That's it. That's all the space we've got. And with 100 watts or so of power. So running an hour, well, here's the thing. Fortunately, that 100 watts goes into a battery. Okay, so you can store it up for the better part of the day and then burn it all, use all the battery power in a few hours, which is what we do. And so we actually run on about 300 watts, but we only do it for a few hours, and we use up the whole day's supply of battery juice, of power for the rover. Everyone else can take a day off when MOXIE is running. And of course, we call it a sol because it's not quite an Earth day. So we have a MOXIE sol, and when we run, everybody else, kicks back and catches up when they're asleep. But we can't do that very often because there's a lot of other instruments on this rover that need a chance to run too. We're not the only ones. So when we run, we actually, unfortunately, have to spend about 2 hours just getting this instrument ready to run. And the reason for that is because inside this red box, all right, is something that's called a SOXY, or a SOX, a solid oxide electrolysis system. And honest to God, I'm not making this up. When they made this model, I said, you've got to make this box red because I want to be able to point to the Red Sox because I'm from Boston. Okay. So that's our Red Sox right here. And for that to work, it has to heat it up to 800 degrees centigrade, which is very, very hot. And that's what takes a couple of hours to do. And then once we're there, we've used most of our power. So we spend about an hour actually making oxygen, and then we call it a day. And then we do that again a couple months later because the rover has to drive, we have to collect samples, the other instruments have to run. So that's what we're doing.
Wow. So the heat is part of the process of extraction, I suppose, or conversion. And
That's right.
for all of us in the US, I always tell my students this: it is time for us to convert entirely to metric, because metric is the language of scientists. But when we're talking 10 grams, we are literally talking 0.002 or 0.22 pounds, maybe. It's very tiny, people. That's all I know.
Yeah, I mean, if you had like the definition of a gram, a cubic centimeter of water weighs a gram, and that's about the size of a sugar cube. So a couple of sugar cubes of water is a couple of grams.
Couple of grams. All right.
Yeah.
Any other hopes for this mission? So it sounds like all the other instruments, RIMFAX, Sherlock, all those are like, take a rest, guys. No chem today. MOXIE's going to be running, but how many times will you do it? How many times will you run that experiment?
Well, of course, we don't plan the whole mission in advance, but we do plan sort of a strawman mission. And what we want to accomplish, the main thing we want to accomplish, is to show that this instrument is rugged, that it's robust, that it's resilient. And for us, that means, can we run in this? Mars has seasons just like Earth. In fact, even more so, they're more exaggerated. It gets very cold, the days get short, it gets warm, the days get longer. But more also, the atmospheric pressure drops a whole lot in the spring and the fall, because literally the atmosphere is freezing out on the North Pole of the South Pole, shortly after at the end of the winter on either pole. And so if there's less pressure, there's less air for MOXIE to use, and sometimes dust in the air. So we want to sample different times of year. And so what we're planning to do is to run every couple of months through the year, and remembering that a Martian year is almost 2 Earth years, okay? So every couple of months spread through the year is going to mean, not 6 times in a year, but more like, 10 or 11 times in the Martian year. And that's our plan going in. Now, reality, I expect we'll run a lot more than that, because MOXIE, unlike anything else on the rover, it doesn't care where the rover is. It doesn't care whether arms are moving, or what, because we're sitting comfortably in a nice warm belly in the rover. We just need to draw in air. So I suspect there will be times when, for different reasons, other instruments aren't interested in running. There's nothing new here. We were here yesterday. And MOXIE will say, well, we can. So we'll see. We'll see. It's not the plan, but, Eisenhower, I think, made famous the expression that plans are worthless, planning is everything. So that's what we're doing. We're focusing on planning, not on plans.
It's always surprised me that in any given NASA mission, and especially the rovers that have gone onto Mars, the hope or the intention was 90 days, say, for Spirit and Opportunity, and they both defied and went brilliantly past those, kind of hallmarks or benchmarks, I should say. So I have every reason to believe that you are correct. You're going to get a lot of chances to try this thing out. But when you start talking about time, let's talk about time on Mars. Next week, your life really shifts to Martian time as you guys sort of count the days and everything as you're watching this mission unfold. How exactly do you live in or on Martian time?
That's a great question. It's a question that fascinates all sorts of people, including people that study, biology and psychology and human behavior, which underscores the fact that if anyone in your audience wants to get involved in going in the space program and exploring Mars, you don't need to be an experimental physicist. You can be a physician. You can be you can be a researcher of all sorts. You can get involved in testing of human behavior. Human beings are generally locked into the cycle of light and darkness on Earth. That's why we get so jet lagged when we go from place to place. And Mars is really fascinating in that it is almost like Earth in the sense that its day is almost the same length as Earth. It's just a little bit longer, just a little bit, 37 or 39 minutes, depending how you measure it. And so if you always want to get up with the sun on Mars, okay, that means that every day on Earth you need to get up 37 minutes later. And I like to look at it that way. I'm the only one. I said, this is great. I get to sleep late 37 minutes every day, more later than I did the day before. Isn't that great? Most people find it much more disturbing than that because their light-dark cycle is messed up. It's not so much the 37 minutes. It's like being on the shift one day and 2 weeks later being on the day shift. Every day, or moving around the globe and traveling one time zone or half a time zone every day, that's pretty wearing. And for those of us that have a life, as most of us do, and have kids to take to school or doctor's appointments or who knows what, you can't quite just say, well, it's okay. Tomorrow I don't wake up till 6:30 in the evening, so too bad about school. You can't do that. So it's stressful. And so you say, well, then why do we do it? Well, an important thing to realize about Mars, people always ask, what's the time lag when you talk to Mars back and forth? And I answer, if you're on the surface, on the rover, it's not about the time lag. It's about how you talk to Earth. And the way you talk to Earth is actually through a relay, meaning on the ground, you use a local, something like a cell phone, okay, to send your data and your information up to a satellite. And that satellite is going around Mars, and that satellite in turn will relay the data back to Earth when its time comes around. So it can be hours. And typically what you do then is to say, okay, it doesn't really help me to talk to Earth too often because I have to give the rover instructions. I have to wait until it carries them out. And then I have to get the data back so I can make the next set of instructions. So you can think about it this way. Okay, when the sun comes up in the morning on Mars, the first thing we do is we talk to it and we say, hey, here's what you're doing today. Here's your assignment for the day. So we have to prepare those instructions very carefully. Okay, there are no do-overs, right, on Mars. If you mess up the rover, game over. You send up the instructions in the morning, you take the rest of the day and let the rover do its thing, and then in the evening you come back and get the new data down, and you now have to scurry like mad all night long, and I mean Mars night, to get the commands ready for the next day. And then you can sleep while the rover's working in the Martian daytime. And why does the rover have to work in the daytime? It's not solar powered. Well, it turns out, even though it's not solar powered, power is precious. It's precious. And it costs a lot more energy to run at night when it's colder than it does during the daytime. So we naturally settle in on mostly a daytime cycle of operation. And we let the rover sleep, recharge its batteries at night. And by sleep, it means it basically turns everything off except a clock that keeps ticking. And recharges its batteries. So we're locked into it. The rover is locked into a Mars day-night cycle, as you might expect. And we're locked into the rover. Now, in practice, we'll do that for a month or 2 or 3. And then we'll go to Earth time ourselves and just live with the fact that sometimes when we send our instructions up to Mars, the rover won't do it till the next day. We don't want to start that way, but we'll ease into that after a couple of months. And then we can all go back to our normal life schedules.
Do you miss Martian time once you go back to Earth time?
That's a kind of a funny question. I would say most people say, oh God, no. It was miserable. I did it once on the Phoenix mission. I had the advantage that the mission headquarters were in Tucson. I was living in Los Angeles. And so I didn't have any family commitments, etc. I had nice dark blinds on the windows, and it's too darn hot in the daytime in Tucson in the summer anyway. So I was happy to be awake at night. But more than that, it was one of the most exhilarating times in my life. I mean, it's just so hard to describe to someone what it's like to land on Mars, and everything you do every day is the first time anyone has ever done it. So I can't separate that from missing Mars time to missing that extraordinarily exhilarating experience. Okay, it's all muddled up in my head.
Talk to students out there who are listening about just the joy and exuberance that you just kind of described, that there's just such walking in your purpose, walking in this kind of like path of exploration and new discovery. That what is that like, and why would you encourage them to do something in STEM? Because what you're describing sounds like the grandest adventure ever.
It's almost hard to know where to start. There are so many reasons it's a grand adventure. I mean, there is something in our DNA, right, that tells us to go out and explore, right? That to go places no one has ever gone before. And my God, going to another planet. You know, I walk out at night, especially when we're on the way to Mars, because I won't go into the orbital mechanics, but when when a spacecraft is on the way to Mars, Mars is really bright and red in the sky, and it looks so close you can reach out and touch it. And when I go outside and look at Mars in this period, and I know we're getting closer and closer every day, it really does feel like we can reach out and touch it. And it really does feel like, in a sense, we are going there and setting foot on not just another country, not just another, desolate place, but an entirely new world. Okay, that alone, the questions we are asking, are enormous. The question of whether there is life on Mars is not just a question of whether there is life on Mars. It's whether we are unique, being alive in the universe, because we don't know from just being one planet. We could be unique. We could not. If we find life right next door, well, gee, we can figure out that life is everywhere, and we are very far from alone. We're in a very crowded universe. So we're looking at big questions. If you're looking at with geologist eyes, I'm not a geologist. I'm more interested in climate and polar stuff, but most of the people on the mission, excuse me, are geologists. And when you look at Mars, here's what you see. When you look at Earth, here's what you see. You see a lot of trees. You see a lot of water. You see a lot of surface stuff that's all fairly new, that's come from rain and planting and trees and growth and tectonic plates. When you look at the surface of Mars, you're seeing history going back 4.5 billion years. In fact, our landing site in Jezero crater itself is about 4 billion years old, and most of the things we're looking at go back to about 3.5 billion, right? Not million, billion. And the terrain we'll be covering could cover another couple of billion years to what's fairly modern. It's only 1.5 billion years old. And you can imagine, to a geologist interested in how planets evolve and how rocks and minerals form and evolve over time, that's a playground. That's a candy store. That's extraordinary. And just the sheer magnitude of the enterprise. You're talking about talking to students about why they should get involved and how to get involved. This doesn't take a village. This takes a city. This takes a community. This takes a country. This takes literally thousands of people with expertise ranging from how to weld two pieces of metal together, to how to make how to make a logo, to how to build an instrument, to how to interpret a scientific result. And when I tell students, how do I get into this? I say, first, figure out what you love doing. First, figure out whether you want to be an electronic engineer or you want to be a radio show host. There's room for you, whatever that is. And then once you do that, well, then stay involved. There's so many ways to stay involved. As kids, from space camp to sort of summer internships when we get older, to programs like yours. So the discipline is not important. Being an experimental scientist is not important. What's important is having all of these different talents and abilities available. And that's what I find exhilarating. Working with people in a common cause of such different backgrounds and interests and skills, I don't know what can be better than that.
Wow. I have to ask, who was the biggest influence on you becoming a scientist? Where was that beginning of your hero's journey to where you are now? Was there a person? Was it a family member? Was it an event?
I'd like to say it was, and I guess I could point to a couple of events that convinced me this was the way to go. But for most of the people I know in this business, okay, the answer that they will tell you in a more unguarded moment, right, is that they were science fiction fans growing up, right? Really, and I devoured everything I could find. I was just pulling out when I was a kid. I was really into the Danny Dunn series, which you never see today. Boy Scientist. And then we go on to Star Wars and Star Trek and Ringworld and Heinlein and all the greats and Asimov and Ursula Le Guin and everyone else. And man, if you can't read that stuff, month after month, year after year, without saying, I want to do this for real. I don't want to do this for make believe. I want to do it for real. So I think I was no different from others that way. That the science fiction inspired me. I may have mentioned. I mean, when I was a kid, Neil Armstrong set foot on the moon for the first time, and you can't find anyone who didn't have their TV turned on at that time. Watching Neil Armstrong say, "One small step for man, one giant leap for mankind." That influenced all of us to say we can do great things. And someday, I'm hoping someone in your audience will be the first person to set foot on Mars, and she will say, "One small step for a woman, one giant leap for humankind."
And I did something. We designed our own Mars mission patches, thinking about the Artemis generation, and soon hopefully we'll go back to the moon with the first woman and the next humans, and then on to Mars. And for me, it's like when I think and talk to students about what that's going to be like, it's going to be one shared experience. It won't just be one country. It's going to be a collective, and it's like it will be for all humanity, and it will be this one time when we're all taking that step, having this first experience together. And so I'm going and I'm waxing poetic, and as I'm telling them this, I'm showing that some patches have Latin. Is there something they want to kind of translate from English to Latin? Do they want to mention their crewmates, etc.? And one such beautiful, again, the kids will always blow you away. But one little third grader put the Friendship Express. That was going to be the name of her spacecraft that was going on to Mars, was the Friendship Express. And I said, "Why did you call it the Friendship Express?" And she goes, "Well, you said we're doing it for humanity, so I want the whole world to be our friends." And it was just, again, that beautiful, simple and beautiful childlike faith that the Friendship Express is headed to Mars. And so I know that in many ways, across all the many people, and you're talking thousands upon thousands and partnerships and things that you've done, it really is the friendship. Perseverance, I suppose, is the Friendship Express going to Mars.
Oh, it sure is. And of course, we do look to, particularly to kids, to name our missions just for that reason, because they see things with eyes that it's hard for us to, it's hard for us in a way that it's hard for us to do. And the name Perseverance and the names before that have come from open contributions of students everywhere. And this mission, more than any I've seen, reflects that international nature, not just because we have international contributions on the mission, and of course we do. The sample return, the way we will be collecting samples that will be returned in a very complicated mission that involves a lander and a rover and a launch vehicle and a rendezvous and bringing things back to near Earth and then sending them down to Earth. And NASA is already planning that with lots of countries and countries in Europe. And boy, if you just look at this week, look at this span of 2 weeks. And a few days ago, the Hope spacecraft from the United Arab Emirates arrived at Mars. And I read today that the Chinese spacecraft arrived safely and got into Mars orbit. And they're looking to send a lander down in a few months from orbit. And we will, of course, arrive a week from today. on the 18th. So 3 different countries leading efforts to all go and study the same planet, and we all talk to each other. Even the spacecraft talk to each other. When I say relays, often we're relaying back data to Earth through another country's spacecraft. So it is absolutely, in every sense, become an international adventure. What an advance, what a change from the days of Apollo, where it was all about national pride and showing we're better than anybody else. No more. Now it's about friendship, hands in hand, exploring the unknown. And I find that inspiring.
I find it just wonderful. It was, I watched and waited while the Hope probe was attaining orbital insertion. And then, TON-1 did so successfully. The Chinese did that just, I guess, in the last 24 hours or so.
Right.
And when you think about all of the names that are going, we've got Hope. We've got TON-1, which TON I read is like, I believe it means questions of the heavens. And then we've got perseverance and ingenuity. And we've got MOXIE, a lot of vim and vigor. It makes me, I think I'm going to have to ask you, Michael, to send me some MOXIE down to Tennessee. We've got RC Cola, but we do not have the MOXIE tonic. So I'm going to have to try that out. Any last words just on what it means to do this kind of science as a physicist, to watch your team, to guide it, any kind of other insights about this mission and how we can find out and make sure we're following all the updates on MOXIE?
Well, there's a few questions mixed in there. Let me start with the insight as a physicist. What I have always found so fascinating about studying this planet in particular, I like to say Mars is my second favorite planet. You can figure out what my first is because it is so similar to Earth, yet so different. And it makes me aware of things that we all just take for granted, like what I just told you earlier, that we need oxygen in order to use fuel, something we never think about. And I'm constantly discovering things like that are part of the equation of how things work, which is what excites me, is figuring out how things work and recognizing that, well, they don't always work the same as they work here. And you just have to change things a little bit in the gravity, in the atmosphere, in the pressure, and everything works differently. And I find that fascinating. As far as where we're going and the mission, well, there's lots and lots. I mean, the internet is a blessing here. There are so many ways to participate, so many ways to watch, and so many ways to get involved. Everyone should just tune in when we land next week. And of course, I never want to be cocky about this. I know we landed Curiosity successfully, and it's just about the same spacecraft, but we did it once, right? We did it once. You can flip a coin twice and get heads the first time. It doesn't mean you will the second time. So we're getting pretty good at this stuff, but it's still really, really hard. It's still really daunting. And I'm certainly old enough to remember and have been involved in missions that didn't work. So they don't call that landing 7 minutes of terror for nothing. And it's not just that it's hurtling down through the atmosphere at breakneck speed and then coming to a stop at exactly the right time, not too high above the ground and not too high far below the ground, if you will. That's really hard, but it's terrifying because we know this is not slam dunk. This is hard, and we believe we can do it. Okay? And I'm looking forward to doing it. But I'll be watching every minute, biting my nails. And I think everyone else in your audience will be doing the same thing if they tune in. So please do. Please join us.
Please join us and watch and follow along. I want to remind you of your own words here. You gave this quote and you said, when we send humans to Mars, we will want them to return safely. They're going to need to lift off the planet. And what MOXIE is doing here is that literally we're going to find out. We know that it works here in 1G. Let's see if it works in 38% gravity there. But if MOXIE can transform that 96% carbon dioxide into some kind of liquid oxygen propellant. I mean, pack your oxygen tank, astronauts, and let's get ready for Mars, right?
Let's get ready for Mars. I like to think that it's going to bring that day 10 years closer, successful. And that's what motivates me to do this.
Well, thank you. Thank you for your brilliance. Thank you for your vision. Thank you for your love of Mars. And I think MOXIE is exactly, not only do you exude it and exhibit it, but we are rooting for so many of these instruments on Perseverance. But MOXIE has been one of my favorites to, help kids understand what this is and what a game changer in exploration that it's going to be. I'm going to err on the side of like overconfident optimism, and I can't wait to see all of these things work so successfully. Thank you so much for your time. Thank you, everyone. Please follow along the Perseverance mission. You can find out more on our website, on MOXIE. Again, you don't have to go very far, just Mars and Perseverance and MOXIE. You can find out even more, and it'll even give you more kind of fine-tuned details there. But Michael, have a great, great day. Thank you so very much for being with us.
Well, thank you so much for the chance to talk to your audience, and I'm so grateful for what you do, because it's as much a part of the mission as what the scientists on my team do. So thank you.